Alrighty, ladies and gentlemen, we're at 4.4, trig functions of any angle. Okay, our objective here is going to be evaluating the 6 trig functions or solving trig-based problems based on the various given information. Now granted here, just to avoid the redundancy of the directions, unless otherwise stated within this stuff, the directions are basically to find all 6 trig functions based on, and then whatever I give you. So hopefully that doesn't mess you up, but here we go. Okay, so the first part, again, since I didn't specify otherwise, we're going to find all 6 trig functions of this angle based upon a point on the terminal side of the angle. So basically what we've got here is our angle that's been opened, such a radian measure or degree measure, it's actually irrelevant, such that our terminal side passes at the point -3, 1. Alright, well what that allows us to do is kind of imagine ourselves a nice right triangle through here. Alright, so if this is -3, 1, that puts my horizontal at -3 and my 1 is my vertical. And then Pythagoras will let us know that this is going to be a √10 right there. Alright, so basically from there, and I think I don't need to do every single one of these, but again, if this is our angle theta right there, then sine of theta is basically, again, just use your SOHCAHTOA, you know, opposite over hypotenuse. So 1 over √10. Okay, of course, that's going to need rationalizing. Sorry, the 1's hard to see right there. And so that becomes √10 over 10. Alright, then I'll do cosine, and then I think we can probably stop from there. The cosine is going to be the adjacent over hypotenuse, so that's -3 over √10. Again, a little bit of rationalizing later is going to give you a -3 √10 over 10. Alright, point being is that we don't have to have all those nice pretty pi over 3, pi over 4 angles. We can just have whatever, and as long as you can construct a triangle, you can go from there. Again, I'll say etc. at this point. If you need me to explain the other 4 to you, please get me in class and I'll be happy to do so. Alright, now moving on, it's time for America's favorite game show, Name That Quadrant. Alright, well, anyway, as the goofy heading implies, basically I'm going to have some information here, and we're going to have to decide what quadrant or quadrants are being referred to. Alright, so anyway, if I've got sine greater than 0, okay, and again, here's maybe a good time to have that crazy all students take calculus thing in your head. Okay, so sine greater than 0, again, now let's say sine is positive. So if sine's positive, I'm going to underline this in red for effect here. Okay, sine's positive, and notice the first and second quadrants. So sine being positive, and you can do this with shading, or you can do whatever. I've got that. Okay, now let's pick another pretty color here. Now if secant is less than 0, remember secant goes along with cosine as far as positive versus negative. Alright, so cosine is positive in the first and fourth quadrants, although we want to be negative here, so basically what we're talking about is now the second and third quadrants. So secant and or cosine is going to be meeting this condition in these 2 quadrants. So basically the quadrant that I'm concerned about, notice as the overlap, is quadrant 2. Alright. And basically just whatever given information, look at what quadrant or quadrants apply to that particular given information, and then answer the question accordingly. Okay, now I actually do say it in this case, but here we go. I'm going to find the trig functions if, and then there's a set of conditions. Okay, I've got a cosine given to me already, so, well, obviously I already know cosine, and as long as I'm not brain dead, I know secant. But mostly what I want to talk about in this particular problem is that statement right there. All we're again is saying is this theta right here is somewhere between pi and 3 pi over 2. So in case that's throwing you, here's the explanation. Well, pi would of course be kind of the 180, so kind of the negative x direction. 3 pi over 2 would be down here in the negative y direction. So it's somewhere between those two. So this is just a fancy way to say, hey, I'm going to be in quadrant 3. Okay, so now going back to my cosine statement, if my cosine is -5/13, again, this is my adjacent and my hypotenuse. Anytime you're dealing with cosine, that's what you're dealing with. So I know I've got a -5 as my adjacent, as I draw my angle into the third quadrant here, and then my hypotenuse, which is again is more like a radius in the circle, is going to be 13. And if I know my Pythagorean triples, I know if I'm making this guy a 13, I know I'm making this guy right here a 12. Although do pay attention to the direction we just went, because when I'm down in the third quadrant, that does mean that I need a negative y coordinate as well. So basically there's my triangle, and then from there I can just start doing my other trig functions. So sine is the -12 over 13, and again I think I can kind of say etc. at this point. Again, I've already got the cosine, And again, just doing all the regular SOHCAHTOA stuff, you should be able to get all 6 of them without too much trouble. Alright, now on the surface, this problem here might look just like the last one, and maybe even possibly easier, because instead of giving us some crazy inequality, I'm actually telling you what quadrant we're going to be in. Alright, the trick of this one is when we do the secant, theta is negative 25/7. Well, again, first thing, hopefully, maybe you do, well, maybe not necessarily hopefully, but maybe the first thing you do is you take the reciprocal of that guy, so it's 7 over negative 25. And you might have done something differently in your head right now, but for the sake of argument, let's pretend that you didn't. Okay, so again, I want to be in quadrant 2, and I want my adjacent over my hypotenuse to be 7/25. So my adjacent's here, and then my hypotenuse is 25. And again, if you know your Pythagorean triples, you know that this is going to be a 24. Now, hopefully you're not just blindly labeling things as you see it here, because notice if I put the negative on the 25, the hypotenuse is more of a radius, which is a distance, which is never negative. So basically, the only thing I want to talk about in this problem is your hypotenuse is never, and I mean never, a negative measurement. So some negative answer here has to be because of one of the other two sides being negative. And in this case, again, hopefully it's pretty obvious because we did go left here with the 7, is because you've got a negative 7 as your adjacent, and then the 25, notice it's still positive, to give you the negative 25/7 as your original problem. Okay, the 24 is positive because it is going up, but again, once you get that far, you can do your sine is 24/25, and again, at this point, I trust you to be on autopilot. Alright, now we're still trying to find the 6 trig functions, but we're giving kind of a weird condition here. The terminal side of some angle lying on this line. Okay, well, one important condition for this problem to actually work out is the 0 right there. If I give you another number besides 0, this would become a whole different problem and be a lot more complicated and actually have multiple answers. So, that's going to be a 0. Okay, now, first thing first, of course, we're going to graph this. I'm assuming most of you are thinking, hey, let's get this guy in a slope-intercept form. So, you subtract the 3x and then divide off the 2, and you get something that looks a lot like that. Alright, so of course, you know, we can get a nice graph right here, starting there, and then we've got negative 3, positive 2, and we get our next point right here, and again we can do that for decades. Another condition of this problem is that we're in quadrant 4, because that's important, because right now if I go this way, but I can also go back to the left and it'd be in quadrant 2, but I honestly don't care about that. What I care about is this. Pretend that's straight. Alright, so anyway, this now is the point. Notice that's 2, negative 3. So this looks a lot like the very first example of this, where I'm giving an angle and I've got some point on the terminal side. And so that's really all that's going on here. You could use this point, you could use other points. Of course, if you went to 4, negative 6, that would work just fine as well. But realistically, what's the point? So again, if it helps you, draw out the full triangle, label things appropriately, 2, negative 3, get some Pythagoras going to get root 13 as our hypotenuse, and then again, just do your regular stuff from there. Okay, we could also be just given a theta, like this, and in this case, notice that theta, hey, that's more than a full circle. Of course, 360 would be a full circle, so unless you're really, really good at imagining what 840 degrees would look like if you just started here and went 90, 180, etc., and kept going around, maybe a good idea is to take that 840 and then basically start subtracting off full circles. And depending on how good you are, you can just subtract 1 360 at a time, although hopefully you realize that that 360 isn't going to be big enough to get us within one circle. 0 to 360 is what I mean by that. But subtracting here, we get 14, that's 8, and 7 minus 3 is 4. Okay, right, now it's still above 360, so if I'm still above 360, I'll subtract it again, and by doing so, I get myself down to a 120. Alright, and then again 120, and again if you're thinking radians at this point, hopefully you're thinking that's 2 pi over 3, although maybe I'm optimistic at this point, but whatever the case, that really puts us right about there, and our good old unit circle values come into play because that does happen to be a very, very nice angle measure. Okay, so once we get to that point, of course, that's our 1/2, but notice it's going left, so it's negative, root 3 over 2, and again, technically you can think of that as the 1, because now we're thinking unit circle values, and now you've got it in there. But basically the point being is if you have something beyond 0 to 360, simply subtract 360s until you get to a point that's nice. Of course, we could have subtracted 720 right from the start, But basically just do whatever you think makes sense, and if you didn't get the answer you wanted, just keep going until you do. But then, of course, once we're here, we can get all 6 trig values. Don't forget that part of this problem, please. Okay, here's another example that's very similar to the last one, except I'm giving you radians instead of degrees, and I give you a negative instead of a positive. Just throw a little bit of a curve, but hopefully not too big of a curve. Point being is we want to get, in this case, since we're dealing with radians, somewhere between 0 and 2 pi. That's my target measurement. If you're really good at the negatives, maybe we're just actually shooting for negative 2 pi to positive 2 pi. And the important thing is to get our theta figured out where along the unit circle we are, so then we can get all our measurements off of it. Okay, so since we're dealing with radians, and 2 pi is one full circle, what I really want to do now is, and since I'm negative, is now I want to add 2 pi's repeatedly until I get, again, between my target of 0 to 2 pi. Alright, well, first thing first is 2 pi, since I'm dealing with the denominator 4, 2 pi is really 8 pi over 4 for adding purposes here. Okay, so negative 21 pi over 4. If I add that 8 pi over 4, okay, hopefully clearly this is not big enough yet, but I've got myself a negative 13 pi over 4. Okay, so instead of 8 pi over 4, maybe I could add a 16 pi over something 4 or something like that, but whatever the case, take that, keep adding 2 pi's or multiples of 2 pi's until you get to yourself something that you recognize and feel good about. So if you're good at the negatives, you could have stopped at 5 pi over 4, negative, but if you're not comfortable with the negatives, keep going until you land somewhere in the positive realm. So the 3 pi over 4, okay, now I'm getting a positive value, so I know I'm sitting right here at 3 pi over 4, and again, at this point, I get my root 2 over 2, negative root 2 over 2. Again, hopefully it's obvious that those are what you're dealing with because you are dealing with the denominator 4. There's your 1. Place SOHCAHTOA in this guy, or again, use your various x, y, and combinations of x and y to get all the other trig values. So sine is root 2 over 2, etc. Okay, so let's move on now to some equations. I'm going to find 2 solutions for these equations. And notice I'm not restricted to 0 to pi over 2 or from 0 to 90 like we were before. So we're just kind of getting a little more advanced, basically. Okay, and I want to give answers in both degrees and radians because we didn't really specify technically which kind of unit we're using, so let's use both. Alright, so now, first of all, if I've got my secant of theta is 2 root 3 over 3. Well, that implies that my cosine of my theta, which is, again, more user-friendly for our brains, technically 3 over 2 root 3, but hopefully that doesn't take you too long to figure out that that's really root 3 over 2, that's where that started. But anyway, so I want my cosine to be root 3 over 2. Okay, so now again, thinking of my whole unit circle, that's a god-awful bad circle, I apologize, but, alright, so root 3 over 2 for cosine, again, remember cosine is our x-coordinate. Alright, so now let's get fancy here. Okay, so if I want my x-coordinate to be root 3 over 2, his partner needs to be a 1/2. So basically, here's my root 3 over 2. Again, notice it's positive, so I went to the right. If it was negative, I'd have gone left. And I don't care what kind of y I had with me. I just care that the x was positive. So basically, I've got 2 possibilities here for a positive root 3 over 2 in my x direction. So basically, this is where those 2 solutions are going to come from. And again, if this is a root 3 over 2, pardon me for splitting the difference here, I know again my partner is 1/2, so in one case it's a positive 1/2, the other it's negative 1/2, but more importantly, because I am worried about the angle measure right now, I am worried about what these angles must be. And because I'm dealing with this, I should be dealing with a pi over 6. Okay, so in my first quadrant, I've got pi over 6, and in my, well, if I go all the way around, that'll end up being 11 pi over 6. Alright, and so basically there's my radian answers. My degree answers are pi over 6 is 30 degrees, and 11 pi over 6 is 330 degrees. So basically, there's one set of answers in radians, there's the other set of answers in degrees for what theta equals. Now to this point, I'm sure you've been sitting there going, oh yes, Mr. Osborne, I know, but give me some word problems. Well, here we go. Okay, now, let's say that we've got a sales model, this equation right here. So a company's sales for a product are modeled by S, which is the number of units sold in thousands, equals etc., etc., etc. And then the T is months, and T equals 1 corresponds to January 2006. Okay, well, the question we want to know are how many units were sold in February 2007. Okay, so basically the first thing we need to do is figure out this statement right here represents t equals what number. Okay, well, if t equals 1 is January 2006, then that means t equals 13 would be January 2007, so then t equals 14 is my February 2007. Okay, so at this point, we can just go s equals, and basically just typing this in the calculator now. 2.31 plus 0. Icky decimal. Okay, again, there's your 14 showing up the first time, plus 4.3, and then we got cosine of, granted it says pi t, but I'm going to write that as 14 pi, because I just like the way that looks better, and I'm going to put the 6 on the bottom. Okay, now there is one thing that is kind of implied here that isn't really obvious, I think, at least until you get used to it. Given the fact that our angle measure here, because of course cosine, there's an angle, since it's got pi involved, it means that we are dealing in radians. I guess technically it doesn't have to be, but if you notice again, there is no degree symbol involved here, so again, the implication is that we are dealing in radians. So do make sure your calculator is in radian mode at this point. Okay, upon doing so, and typing that mess in, you should get a calculator spitting out something to the effect of s equals 31.438. Okay, and the mess of this is, you might think that it's rounded, but that's actually the exact decimal that comes out of your calculator. Alright, so you might initially say, hey, that means we sold 31 units. But please, baby, pay attention, this units is in thousands. So how many units were sold in February? That's that number times 1,000, so it's actually 31,438 units. And there you go. So basically, moral of the story, pay attention. We might be dealing with radians for your measure. Of course, if they are given degrees, make sure you get in degree mode for your calculator. And then do make sure that if your units are given in some kind of other measurement, make sure you do that adjustment for your final answer. There you go. Alright, so here's our assignment. Okay, again, please focus on the odds and do enough of them. I do realize that some of this does get a little repetitive, so I'm not going to torture you by making you do every single one of them. Once you get the hang of it, make sure you do kind of a harder one per section or something like that at least, but skip around, make sure you do what you need practice on until you make sure you are the master of this stuff. Alrighty, there it is, and we'll see you in class.